So today our topic will be linear non-homogeneous PDE with constant coefficient. So far we have been discussing about the homogeneous PDE, right? But in this video we will be discussing the case for non-homogeneous PDE, right? And as we know that what is a linear PDE, that is means every term of that PDE has degree 1, then it is called linear PDE, right? And as we discussed for homogeneous PDE, that was when every term of the PDE is of same order, right? And if it is not the case, then it will be called non-homogeneous PDE, right? Means a linear PDE with constant coefficient will be called as non-homogeneous if every term of it is not of the same order. Let me write an example of it. For example, del square z over del x square, this is the second order derivative term, and plus del z over del y equal to x. This is an example of non-homogeneous PDE because for this term this is second order derivative while this is a first order derivative, right? That's why we are calling it as non-homogeneous. And obviously it is a linear equation because every term is of degree 1. See here, 1 and 1. So that's why it is linear, right? Okay. Now writing in the same way in terms of operator FDD dash, consider f of d comma d dash z is equal to capital G x comma y, where this FDD dash is a linear non-homogeneous operator in terms of d and d dash. Okay, and let me write it equation number A. Okay, but remember that this is a non-homogeneous linear operator. Okay, then for g x comma y equal to 0, if I put this equal to 0, I will be getting f d d dash z equal to 0, equation number B, right? Now how to solve this? I mean, how to find the solution of this non-homogeneous linear PDE? And the method is obviously the same as we discussed in our last lectures for homogeneous PDE, but there is a small difference. And let me write the first to write the factor this FDD dash in terms of linear factors. Okay, so we will have actually two cases, case 1 and case 2. Case 1 is that when f d comma d dash can be factorized, expressed as product of linear factors like d minus md dash minus alpha, let me write it 1 alpha 1, d minus m2 d dash minus alpha 2 dash dash, and d minus mn d dash minus alpha n z equal to 0. So these are linear factors, right? And see here d minus m1 d dash, but this time we are having this constant alpha 1 and here alpha 2 and so on, correct? Then actually each factor is a linear factor, right? And the solution corresponding to each linear factor will be the solution of this equation number B, right? Means first I will take d minus m1 d dash minus alpha 1 z equal to 0, I will solve it, find a solution, let it be suppose f1, and secondly I will take this factor z equal to 0, I will find the solution, let it be f2 and so on. Then adding those solutions will give me the solution of equation number B, right? So then consider, should I write the solution first? Then the solution is given by z is equal to, the solution corresponding to this term comes out to be e to the power alpha 1 x, right, and f1 y plus m1 x plus e to the power alpha 2 x for this term, f2 y plus m2 x, and plus dash dash plus e to the power alpha 3x fn y plus mn x. This will be the solution, right? And it has been written, if considering the fact that m1 m2 m3 and these all linear factors are distinct, right, means none of these two factors repeat, okay, and this were repeated distinct linear factors, right? Or I will write the case for repeated linear factors. Z is equal to e to the power alpha 1 x f1 y plus m1 x plus x times e to the power alpha 1 x again, right, alpha 1 x f2 y plus m1 x. Means if two of these factors repeat, this factor repeats twice, right, and then all factors are distinct. This is for repeating, this repeating factor, okay, plus then f3 y plus m3x plus fn y plus mnx, right? So I have written two solutions. This is for distinct factors, for distinct factors, right, and this is for repeated factors, for repeated factors twice. Repeated factors twice means I have written this solution for only repeated factors, this factor being repeated twice, okay. You can generalize it for repeating it thrice and so on, okay. So I will put a box on this, will be proving this, and the second is that. Okay, for d minus m1 d dash minus alpha 1 repeated factors twice, okay. Let me give a small proof for this solution, right, how this appears for distinct factors. Proof for this one, first one, right? Okay, let me write it small a. Proof for small a and small b. This is small a, and this is small b. Okay, first we'll be proving this a, solution number a. Okay, since each of these factors, right, should be equated to 0, and that will give rise to first order first degree differential equation, right? Consider take any of these factors. Suppose I take d minus md dash minus alpha. I am taking it general, not m1 m2, for m and alpha general. Okay, z equal to 0, right? Then, or I can write it as dz will be p minus mq is equal to alpha z, and all you know that this is Lagrange's form. And since you already know how to solve this equation, and then you write different Lagrange's subsidiary equation, dx dy upon minus m and dz upon alpha z, I think, right? Then you will take these two ratios, you will get y plus mx is equal to c1, and then we'll take the first and third ratio, right? And then you will get log z is equal to alpha x plus c2. Then you will be getting gives, I'm writing solution directly, gives log z z is equal to that C2 e to the power alpha x, and then C2 will be replaced by some function of that thing that will be to the power alpha x f y plus mx, right? On solving, right? You can easily obtain this. We have done the sample number of times. Okay. So on taking two ratios at a time and solving and then writing solution in this form, you can write this very easily. You will get this. Then see this. This is actually the same, right? I have taken it for m and alpha. If you take it for m1 alpha 1, you will be getting z equal to e to the power alpha 1x f y plus m1x. For m2 alpha 2, e to the power alpha 2x f y plus m2x, and so on. And you know that linear combinations of these solutions will give rise to this solution. Okay. So this is the proof for part A, with solution in this form A, right? Now considering for B case for repeated factors, okay, for B, and to prove this, especially this, I have to take a factor repeated twice. Means I have to consider a differential equation of this form, d minus m d dash minus alpha and then a square. Let me write it twice. Means this factor will be appearing twice here, right? Okay. So I have taken it for 2, right? Particularly for factor repeating twice only. Okay. Now, as we did in our previous videos, this was assumed as a new function v. Let d minus m d dash minus alpha z is equal to v. Let me take it v. Okay. Let it be equation number, no, leave it. And then this substitute this in equation number 1. This equation. Then you will get d minus m d dash minus alpha v equal to 0, right? Let's take equation number 1. This is equation number 2. Now solve equation number 2. Let me write it as on solving equation number 2, and this is quite similar to this one, except the fact that z is replaced by the variable v. Should we write the solution from here directly? Yes, this is same. So on solving 2, I will be getting a solution of this form, that will be v is equal to e to the power alpha x, obviously, and f y plus mx, right? Okay. And okay, fine. Let me write it f1, and let me write what is y plus mx. Y plus mx should be equal to some constant, that will be c1. If you go through the detailed solution of this one, you will see that y plus mx is actually some constant c1, right? Okay, I'm not writing that, just giving the right solution. Then substituting this v here in place of this equation number 1. Then equation number first reduces to d minus m d dash minus alpha, and then z is equal to value of v e to the power alpha x f1 y plus mx. And remember that what is y plus mx? Y plus mx is actually c1. I have to use it in solution of this. Or it can be written as p minus mq is equal to alpha z will be taken on the right hand side plus e to the power alpha x f1 y plus mx. Now this is again Lagrange's form. Okay. Now writing the corresponding subsidiary equations, I will get dx upon 1 dy upon minus 1 dz upon alpha z plus e to the power alpha x f1 y plus mx. Okay, taking these two ratios at a time and solving, I will get y plus mx is equal to some constant, and that is obviously is equal to c1. Okay, and taking the first and three ratios, this gives taking dx is equal to dy upon minus m gives, on integration obviously, y plus mx is equal to c1, and taking the first and third ratio, and dx is equal to dz upon alpha z plus e to the power alpha x, and this f1 c1, right? This y plus mx is replaced by c1. Then I have to solve this equation, and this is obtained from the first and the third ratio, right? I have to erase this now, and remember that we are going to give a proof for this, right? Okay. Okay, then I think cross multiplying them and getting dz by dx, or it gives dz upon dx and then minus alpha z is equal to e to the power alpha x f1 c1. See this form, this is linear PDE. Maybe you read this in your higher secondary course, +2 course, linear PDE, linear, not PDE, ODE, ordinary differential equation, linear ODE of first degree and first order, right? And you know how to solve this equation. Compare it with the dz by dx plus pz is equal to q, right? Then you find integrating factor and so on. Integrating factor will be given by e to the power integration p dx, then alpha, I think that will be minus alpha, d minus alpha, d plus alpha, alpha dx is equal to e to the power alpha x, right? And it should be minus alpha, minus alpha, minus alpha. Okay, that will be appearing inside the integral. Okay, that's fine. It's minus alpha x f x. Okay. And yeah, then solution is given by, and z multiplied by integrating factor is equal to integration of integrating factor multiplied by this right hand side e to the power alpha x f1 c1 dx, and we write plus c2 also. Yes, plus c2, right? I assume that you know how to solve this equation, linear ODE with of first order. You solved it in higher secondary school, class 12th, right? dy by dz by dx plus pz is equal to capital Q. Integration factor is given by e to the power integration p dx, and p is actually minus alpha. Then on integration, I will get this integrating factor. The solution is written in the form z, the dependent variable, multiplied by integrating factor is equal to integration of integrating factor multiplied by this capital Q, which is the right hand side, dx plus constant c2, right? Okay. Then these terms will be cancelled, and I will be getting something like this, x f1 c1, and this will appear here e to the power alpha x. I think I should write it this way, e to the power alpha x plus c2 e to the power alpha x. Okay, and then z is equal to this, right? And yes, is it done? Yes. If I take e to the power alpha x common, and yeah, c2 should be replaced by this constant c1 or c2, c1, okay, c1, or I can write it as z is equal to x e to the power alpha x f1, and the value of c1 was y plus mx, right? Okay, and can we write this c2 as a function of new function of that y plus mx, right? Okay, then I will write it as c e to the power alpha x, and this, especially this c2 should be replaced by the function of y plus mx, because c2 is a constant, c1 is already a constant. Two constants can be related by some function. One constant is equal to function of some another constant, right? So c2 should be related by this c1 by this function f2 y plus mx, right? And this is what we wanted to prove. You can see these terms. See this, where's that term? This term is present here, right? And this term is present here, right? And this is the explanation why we write multiply by x in case of repeated roots. And if if the linear factor gets repeated thrice, then we'll write here x square, x square, and so on, as we did in our last videos, right? So this is a small proof for this. Now we'll go to numericals. 2d dash minus 3 z is equal to 0, right? Okay. Then okay, this is already in factorized form, no need to factorize it, right? You can write it as d minus 0d dash, and this should be written as 0 minus, not minus, plus 1d dash, and this will be d minus 2d dash minus 3 z is equal to 0, right? So what we just need to express this given non-homogeneous linear PDE in terms of product of linear factors, and luckily this time I am already having these as the product of linear factors, right? So now the only thing is to write the solution. Therefore solution is z is equal to, right? For this one you will write, since alpha is missing here, so that will be e to the power 0 x, okay, that will not be written. It will become f1 of y plus 0x, but since 0 is here as a coefficient of x, so I am closing the bracket, okay. And for this is 0 plus d dash, means 0y minus x. You can write it as f2 0 minus x, okay. And you can already write f2x, because there is no difference. I mean, it is immaterial if you write f2x or f2 minus x, right? That is immaterial. You can write it as plus x also, okay. And for this one, and this is especially the non-homogeneous kind of operator present here, and I should write it as e to the power 3x, and for this one f3 y plus 2x. So this is the solution containing 3 arbitrary constants, okay. Then taking another example, now this is relatively difficult than this one. Why? Because in this case you have to express in its factors form, and that is not an easy task, right? So should I write it in terms of d and d dash? Yes, you know all these operators are. What is r? This is double derivative with respect to x. S is mixed derivative with respect to xy. T is double derivative with respect to y, and this is p is del z by del x, del z by del y, and this is z, right? So first I will write it in d and d dash form. We have d square plus 2 dd dash plus d dash square plus 2d plus 2d dash plus 1 z is equal to 0, right? And yeah, okay, I'm going to factorize it, but the important thing is that if you're able to pick up something like, is it a perfect square of something? Yes, no, no, yeah, d dash square 2ab 2 into a into b 2 into, yeah, it is a perfect square. One may or may not pick up, see, or I can write it as d plus d dash plus 1 whole square, but this is not an easy task, right? Because you have to remember this formula and apply in the reverse way, and that is not an easy thing, because first term will be d square, that is a square plus b square plus c square, a square plus b square plus c square, and 2 times of ab this term, 2 times of bc this term, and 2 times of ca this term, right? Z is equal to 0. You have to be very lucky in this method if you are able to write this closed form, right? Okay, first me write the solution, and I will write the alternate form how to speak this factor, right? And then since I have written it as this factor repeated twice, so the solution will be, then z is equal to, say this 1, then it will go e to the power minus 1x, the sign gets reversed, right? f1 y minus x, d takes y and d dash takes x, and the sign gets reversed. And since the factor is repeated twice, so I am multiplying this by x e to the power minus x and writing new function f2 y minus x is the solution, right? But I am putting a star here because not every time you will be lucky to pick up this closed form, right? And let me give another way to reach at this step, how you can reach here without even applying the formula. Okay, so alternate for this, alternate. Okay, let d square plus 2d d dash plus d dash square plus 2d plus 2d dash plus 1 is equal to, what do you want? You want this whole expression as a product of two linear factors. And why it is only two linear factors? Because we are having d square, right? So we want it to be in this form, right? D minus m2 dash minus alpha 2. You want this expression in this form, in this nice form, so that you can write this solution directly. Okay, now see, or d square plus 2d d dash plus d dash square plus 2d plus 2d dash plus 1 is equal to, now multiplying this term, d square, right? And then picking the coefficient of d and d dash, that will be, I think, minus or I can write it plus minus m1 minus m2 d d dash, right? And writing the coefficient of d dash square, I think that will be m1 m2 plus m1 m2 d dash square, and then writing the coefficient of d, yeah, d will be alpha 2 and alpha 1 minus plus minus alpha 1 minus alpha 2 d, right? And then d dash, that will be again same, that will be plus, okay, plus m1 alpha 2 plus m2 alpha 1 d dash, okay, and then constant term alpha 1 alpha 2 alpha 1 alpha 2, right? Okay, now after comparing these two sides, you can get m1 m2 alpha 1 and alpha 2 on comparison both sides, yeah. Then the coefficient of d dash is equal to 2, and here the coefficient of d dash is minus 1 minus m2, that will give you m1 plus m2 is equal to minus 2. And on comparing the coefficients of d dash square on both sides, you will get 1 is equal to m1 m2, m1 m2 is equal to 1, and you can solve them very easily. Gives solve it, I think minus 1 and minus 1 will be the only possibility, m1 equal to m2 equal to minus 1. This is the only possibility you can have, right? And now on comparing the coefficients of d, also d, alpha 1 plus alpha 2 equal to minus 2, yeah, right? And compare this constant only, and alpha 1 alpha 2 is equal to how much? 1. This will also gives alpha 1 equal to alpha 2 is equal to 1. So you have got your m's and alphas, right? But remember that this coefficient of d dash must have to be satisfied, m1 alpha 2 plus m2 alpha 1, also m1 alpha 2 plus m2 alpha 1 should be equal to coefficient of d dash, that is equal to 2, that should be equal to 2. And let me verify that these values are correct. Okay, so I will plug in these values here, m1 multiplied by alpha 2, that is 1, and sorry, minus 1 into minus, something is wrong, d dash, coefficient of d dash, yes, d dash, that is positive, and here it's also positive. Okay, fine. This is minus 1, sorry, minus 1. Now it is correct, I think. m1 multiplied by alpha 2 and alpha 1 multiplied by m2, then you add them, then you will get obviously 2. Also is satisfied. right? And it gives a support that these values are correct, m1s and alpha 1 alpha 2 are correct, right? Okay, then writing this equation, we can write d plus d dash plus 1 whole square, plugging the values of alpha m1 alpha 1 m2 alpha 2 here. M1 is actually minus 1 and alpha 1 is actually minus 1, plugging these values here, and then d then value of m2 is again plus d dash plus 1, z is equal to 0, right? And again you reach at this point, this is star point. Okay, so this is an kind of explanation to reach at this step. If you are not able to identify the formula, okay, I will put a star here, star, then proceed as here. So now taking another example, maybe our last example for this case, example number 3, and that is let me take s plus p minus q minus z is equal to 0, starting from the second mixed derivative, right? And let me write it in terms of d and d dash, d dash plus d minus d dash minus 1 and z is equal to 0, right? Sometimes it is possible to pick up the factor, means if I take d common from here, yeah, it is easy, or take d common out of these two terms, then you get d dash plus 1 and d dash plus 1, and you will have minus 1 here, z is equal to 0, right? Okay, then writing the solution for each factor, therefore z is equal to, for this one d dash is absent, this is alpha, d minus md dash minus alpha, alpha is equal to how much, 1, so alpha e to the power minus x, no, plus x, the sign gets reversed, e to the power plus x, and f1 y, only y, because d dash is absent. Okay, and for this one e to the power minus x, f2 and y is absent, means d is absent, and then minus x, or you can write it as plus x, no problem, right? Because f2 is an arbitrary function. Yeah, so this is the solution, okay, right? So taking our next small topic, I think the case number 2 for this one, we have discussed case number 1 where fdd dash can be expressed as a product of linear factors. But what happens if fdd dash, right, your non-homogeneous operator on the left hand side is not expressed as a product of linear factors? Then what will be the solution in that case? Because this formula can only be applied if and only if you are able to factorize it in terms of linear factors, right? But there may be some operator which cannot be factorized even in this way anyway, right? We will be discussing that case. Let me rub it first. So case 2, and what is that case 2? If your fd dash, the operator on left hand side of your non-homogeneous PDE, and obviously this fdd dash is a non-homogeneous operator, right, is not cannot be expressed, as the product of linear factors, right? Then what happens in that case? Okay, and then the solution to f d comma d dash z is equal to 0 is given by z is equal to that should be e to the power capital A e to the power hx plus ky provided that will take f h comma k is equal to 0. Yes, right. If you are not able to factorize this fdd dash, no problem, then this will be the solution, right? A times e to the power hx plus ky provided f of h comma k should be equal to 0. Why I am writing that? Actually, we should write the most general form, that is actually ai. Let me take it ai, and it should be hi and ki y, and the summation runs for I equal to 1 to infinity, right? This is solution. And we can see a small proof for this. Okay, proof, right? Proof is that if you operate this d to the power r on this e to the power hx plus ky, what will happen? Differentiating it r times with respect to x r times, then the answer will be h to the power r e to the power hx plus ky. And what happens if I differentiate it s times e to the power hx plus ky? That will be k to the power s e to the power hx plus ky, right? And what happens also? D to the power r plus s e to the power hx plus ky. What happens then? In that case, I will be getting something like h to the power r and k to the power s and e to the power hx plus ky, right? And this means that if I have something here f d d dash, some operator here, homogeneous or maybe non-homogeneous, no problem, and then I will be getting the result like this. Means it appears that h to the power r and k to the power s, means r plus s gets distributed over the power of h and k. Similarly, this is a suppose it is a nth order, okay, then it will be like fab fhk, no problem, whatever is the order of this thing, just d gets replaced by a and d dash gets replaced by b, no problem, because you can write this as d to the power r into d to the power s, and then d is replaced by h and d dash is replaced by k. You can think in that way. So fdd dash is generally replaced by fh comma k and e to the power hx plus ky, right? So yes, right. And since you are solving this fdd dash z equal to 0, and in place of z I have substituted this function, right? See that my equation was fdd dash z equal to 0, and in place of z what I am having e to the power hx plus ky. It means I am assuming that e to the power hx plus ky is the solution of this thing, right? Or you can put a big capital A here, no problem, capital A will balance both sides, okay? So you are assuming that e to the power hx plus ky equal to 0, and if it is a solution of this equation, then this has to be equal to 0, right? Or should I put this here? Okay, if z is equal to a times e to the power hx plus ky is a solution of this f d d dash z equal to 0, then it must satisfy this equation. Then using this, let me call it equation number 1, then from first it implies that this has to be 0, f h comma k e to the power hx plus ky is equal to 0, and we know that exponential function is never equal to 0, so f h comma k should be equal to 0, as e to the power hx plus ky is not equal to 0, and this was our condition which was mentioned here, right? If you want this as a solution of this equation, this condition has to be satisfied, right? And why I have written this a here, because multiplying it by a, actually I assumed capital A here, so I have to write capital A. Okay, right, this has to be 0. Obviously you don't want capital A equal to 0, because if you take capital A equal to 0, then you will get a 0 solution. Where is the solution? This solution, you will get 0 solution. Yes, and we are not interested in 0 solution, we are interested in non-zero solution. So as this is not equal to 0 and A is also not equal to 0, to get a non-zero solution, right? Okay, so that's why the solution can always be written in this form, provided you are able to find some relationship between h and k. Okay, now taking example of this case number 2, let example be example number 1, right? But this time I have to take some operator which cannot be factorized in terms of linear factors. Okay, example B, d minus d dash square, the simplest example, z is equal to 0, right? Okay, first you notice that it is non-homogeneous because this is second order derivative, first order derivative, right? And secondly, you notice that it is it cannot be factorized as a product of linear factors, right? Yeah, because only two terms are there and there is no way to take something common, means d and d dash cannot be taken common. Okay, so the only way to search the solution for this kind of equation is this way. Okay, so solution will be, let z is equal to a times e to the power hx plus ky, right? First we will start with this and then at last we will put a summation here and generalize it by putting a small subscript I here, right? It will always be good to do calculation without summation notation. Okay, then substitute be the solution, if this is the solution, then this gets plugged in here and it will give d of z, means then I will write it in detail, d of z, differentiation of z with respect to t is respect to x, a h e to the power hx plus ky, and what do I need? I need a d dash square of z is equal to, differentiating this z with respect to y twice, a, I think k square e to the power hx plus ky, and plugging in those values here, this gives, after putting them here, I will get something common, yes, a, and inside bracket h minus k square e to the power hx plus ky is equal to 0, right? And remember again that this being an exponential function, it can never be 0, and you don't want a to be 0 because you are interested in non-zero solution. A zero solution is always a solution for this kind of equation where the right hand side is 0. Is that okay? Yeah, see this, zero solution is always a solution. If you put z equal to 0, then you are done, obviously, but you are not interested in zero solution, you are interested in non-zero solution. That's why you don't want this a to be 0. You know that this is non-zero, you don't want this to be 0, obviously it has to be 0, h minus k square, or h minus k square equal to 0, or h equal to k square. So this is the required condition what we are searching for, and then I can write the solution. Therefore the solution is z is equal to, I will put a summation because to generalize that, a I, okay, e to the power hx plus ky, and h can be replaced by k square x plus ky. You can put a small subscript I here. This is a solution, this is a general solution. Okay, right. Then taking second example number 2. Let me write it at 2d4 minus 3 d square d dash plus d dash square z is equal to 0. Yes. Okay. Then first you notice that it is a non-homogeneous equation because first this is fourth derivative with respect to x, third mixed derivative, third order, and this is second order. It is non-homogeneous. Second thing you notice that, are you able to factorize it in terms of linear factors? Can you take something common or you can factorize it? Yes, I think we can factorize it. Solution. Let me try to factorize it. 2d to the power 4 minus 2 d square d dash minus d square d dash and then plus d dash square z is equal to 0. Yes, it can be factorized because actually it is a biquadratic equation in D, right? If you focus on D only, do not focus on D dash, then it will be 2d to the power 4 minus 3d square plus 1, or you can think in that way, putting d equal to m and d dash equal to 1. However, that is not mathematically correct, but sometimes you have to rely on that fact to factorize it easily, right? So what I have done here, I focused on d, powers of d, and that were like a biquadratic equation, 2d to the power 4 minus 3d square and then 1. I am not focusing on d dash, right? So factorization can be done easily this way. Okay. Or then I will write it as, or then 2d square will be taken common from these two terms, right? And inside bracket I will be getting how much? D square minus 1, and from here d dash will, no, not d dash, it will be d dash, d dash. Okay, and from that bracket common will be minus of d dash, minus of d dash, right? And z equal to 0. I think I am correct. Yes, correct. But notice that these are not linear factors. It's very important point that these are not linear factors, because see here, d square is present, d square is present. Due to this square and square, these are not linear factors, right? So you can't apply that formula directly for when the linear factorization is possible, right? You have to rely on this, again, this theory, because this is not linear factorization. However, it appears that they are factors, but they are not linear factors. So I have to use that. And for first for this part and then for that part, right? Okay. I will take it one by one. First thing, taking d square minus d dash and z is equal to 0, right? This part. Then I will take second one. And since I see that it is not factorizable or cannot be expressed as a product of linear factors, and again it is non-homogeneous, then I will search a solution of this kind. Z is equal to this kind, right? And if you notice that this calculation, see this calculation, what I have plugged, z is equal to a to the power hx plus ky, and what I have got the condition h is equal to k square, or ultimately h minus k square. You can think like that, because this will be non-zero. That is what you want, and this is always non-zero. So h minus k square, and that is precisely this term, h minus k square. It appears that d is replaced by h and d dash is replaced by k, right? So that is kind of shortcut where what you can apply here. So I will be getting h square minus k based on these lines, right? Taking this, then z is equal to summation a I, right, e to the power hx plus ky, and where k is the okay, hx plus ky, and the value of k will be h square y. Let me put I here, I, right, where hi equal to ki square. No, hi square equal to k, hi square equal to k. Okay. Following this method, I will get this. You can see that it is easily obtainable, right? And this is a solution for this part only. Now focusing on the second factor. Let me rub it first. Taking another factor 2d square minus d dash z is equal to 0. Then what will be the solution? Z is equal to summation, let me write it I, and let me change the constant bi, right, e to the power 2h square is equal to k, means k is replaced by 2h square, hi x plus 2 hi square y, right, and where 2 hi square is equal to ki. Okay, so there is a solution for this factor, and since we have this equation number, suppose I take it 1, then the solution for 1 will be given by the linear combination of these solutions, right. Linear combination can always be used as long as we know that the equation is of linear nature, right, and this is a linear equation. Okay. Therefore solution is z is equal to summation I ai e to the power hi x plus hi square y plus summation bi e to the power hi x. Should I change the constant? Yes, I have to. I should write it as alpha beta, right? No, alpha is used there. K, L or M, L I, right? Where Mi is Li square, right? Z is equal to B, yes, B times e to the power Lx plus My. Yeah, I have changed the constants. Then it will be summation Bi e to the power this one 12 square Li x plus 2 Li square y. This will be the solution, is complete solution, where hi square is equal to k and 2Li square equal to Mi. These are the conditions. Okay. So taking another example equal to 0. So in this example, we have taken one factor which is already a linear factor, see these powers, and another factor is non-linear factor, non-factorizable, right? In this question, they both are not factorizable linear factors, right? And in this question, this is factorizable, already factorized, and this cannot be factorized, right? Solution. Here, d plus 2d dash minus 3 d square plus d dash z is equal to 0. This is our equation. And first, for taking writing solution for this and this, right? Taking this one, taking d square plus d dash z is equal to 0, and since we know that it is non-homogeneous and non-factorizable as a product of linear factors, you cannot factorize it, right? So you have to rely on that solution e to the power hx plus ky. This solution is, should I write the solution directly? Yes, that is very easy. Z is equal to summation I a I and e to the power hx plus ky, where h square equal to minus k from here, right? So hx plus ky, and k is replaced by minus hi square y, right? Taking this one, d plus 2d dash minus 3 z equal to 0. And the solution for this can be written directly. you know that solution is z is equal to e to the power 3x, right? f1 y minus 2x, where f1 is arbitrary function. And then writing the solution, full solution for first, then solution to equation number 1, the complete equation can be given by adding these two. Z is equal to e to the power 3x f1 y minus 2x plus summation I ai and e to the power hx minus hi square y, right? And there is no need to write this h square equal to k actually, because k is not present here, right? So this is the full solution to this equation. Okay, so the number of examples we have done are sufficient, I think so. And in our next video we will be finding the solution when the right hand side is non-zero, right? That will be the part of our next video. Okay, thank you so much for this video. Thanks.